All right, so there's been quite a few questions about how to verify the op amp for lab, I think it's 5. So I decided I'm going to make this video just running through a demonstration of how I would do all the verification with all the different test benches and tests for this op amp. And originally I was just going to do one or two, but I think it'll just be fairly quick just to run through this all and try to put timestamps in or something like that. So you know where to, you can just find the section that's useful for you. Okay, so for lab 5, you're given all these different specifications to simulate. And so I think we're going to be able to do DC gain, gain bandwidth, ICMR, systematic input offset voltage. This is a calculated parameter that's expected 3 sigma input offset voltage. We can do the quiescent power consumption, pole zero plot for the closed loop. So pole zero plot closed loop, and then the pole Q magnitude response of the amplifier in a unity gain feedback configuration, and phase margin in a unity gain feedback configuration, and I think also the signal to noise ratio. We can do all of these with a single test bench if we're smart about how we do it. So I have my empty test bench here. So I'm going to start by instantiating my op amp that I've designed. And this op amp is a 2-stage op amp, just like you guys have. That was weird. Just like you guys have made in your lab. I just have the biasing voltage sources inside the schematic. That's why you don't see them here. So I'm going to connect this. I'm going to do two things in this loop here. The first is that I'm going to go to analog lib and then grab this I probe. Now you can technically do this without it, but it's fine. I'm going to flip it and place it in this feedback loop. Then the next thing I'm going to do is I'm going to grab a voltage source, and we're going to call this VS, or I'll call it uppercase VS, which is basically just like a generic dummy variable that we're going to sweep. And we're going to put this with polarity like that. That's going to go in series, and this is going to connect to the inverting input. And then at the non-inverting input, we'll do another voltage source. And here we'll give this reference this to ground. And then we'll give this call this VCM for the DC voltage so we can have control over it, but we'll probably just make it 0. Give it an AC magnitude of 1. And then that should be all that we need. What we're going to do is, of course, always add our load capacitor. So I think it was 20 picofarads for this lab. I'll put that on our load and then ground it. Okay. And then, oh, one more thing we need to do. So let's move this down, or let's delete it. I also want to add one of these sources with VS into this point right here. Okay. Oh, and I forgot my, oopsie. Of course, you always need your VDD and VSS. So I'll set those up. Oops. Like that. And then make this VDD, and this I'll give it a variable VSS. Okay, now everything is all set up and ready to go. So the purpose of these sources here will be to sweep the common mode input voltage for our ICMR test while keeping the output at like 0. It just makes it a nice, easy to read output plot, as opposed to other methods. Just make it a little bit trickier to measure what you want to measure. This iProbe is like I think it's supposed to be like a current probe basically, but it's used for stability tests for defining where to break the feedback loop to measure the loop gain. So that's what that's for. Okay, so let's start off with our setup for DC gain, gain bandwidth. Yeah, let's just start working on this. So we're gonna go launch ADE Explorer, create a new view. And the first thing I'm gonna do is because I'm using a MIM cap as a compensation capacitor in my op amp, I'm gonna go to this setup model libraries. I'm going to copy one of these entries here and paste it. Then hit this little dots button. And I'm going to find the core_mim.scs, select it, and then this drop down over here, select TT-mim. So it's a typical corner for the MIM capacitors. So if you don't do this, you'll get a simulation error. This is telling it where to find the models for the capacitors. And the first thing I'm going to do is set up an STB analysis, which is a stability analysis. I'm going to sweep the frequency from 1 Hertz to 100 megahertz. Logarithmic, I'll do 50 points per decade. And then for probe instance, do single-ended, hit select this iProbe component. And then I can go back to this. And then for my local ground name, select, and I'll select this ground net here. And then I can click OK. And so what the stability simulation is going to do is it's going to break the loop at this iProbe, and it's going to measure the loop gain, which if you remember from like classical control theory is the open loop gain, or it's going to be the gain of the op amp, the open loop gain, times the feedback gain, which in this case we're going to set VS to 0 for the simulation, so that then the feedback gain is just a unity gain feedback, so it's 1. So that means when we measure the loop gain, which is A times beta, beta is 1, so we're really just measuring the gain of the op amp A, or the open loop gain. The reason we do this instead of just an open loop simulation is that the biasing of the second stage of this op amp gets a little touchy, and so it's easier to put it into feedback, so that the feedback will kind of auto bias the amplifier. Yeah, so I forgot to set the design variables, so let's do click to add variable, copy from. I'm going to set my common mode input voltage to 0. VDD is 1.65. VS, I'm going to set to 0. So this is like the typical value if it's not specified in the test. And then VSS will be negative 1.65. Okay. So let's grab our stability results. So if we run our simulation, I'll do this. I could set up all this tests at once and then go through how to look at the results, but let's do it one at a time. We'll just kind of add tests in as we go. Okay, so completes with 0 errors, 0 warnings, perfect. Go to results, direct plot, main form. Make sure you have the stability selected. And then I want the loop gain, magnitude and phase, dB20. I'm going to check this little box to add to the output so that in the future when I simulate it, it'll auto plot it. Then I'll hit plot. And here you can see the loop gain, which for my case, again, is going to be open loop gain. Or it's going to be the open loop gain because we have that beta of 1. Now we have the phase response. So from here, I can read off my DC gain from this point, and then I can find my bandwidth, and then I can find my like unity gain frequency or gain bandwidth. So what I'm going to do is I'm going to close this out. I'm going to leave this up and come back to it later. I'm gonna go here, and now that I've got these two things here, I'm going to add a thing called DC gain, which will be value of the loop gain dB20 at 1 hertz, because that was my minimum frequency. And this will auto measure my DC gain, and then I'm also add my bandwidth, or I'll call it my gain bandwidth, which is going to be equal to, let's see, I need my DC gain in volts to volts. So let's do 10. Exponent is 2 asterisks. So 10 to the DC gain divided by 20. Then that's going to be times, and my bandwidth is going to be the point on the loop gain. The loop gain plot where it crosses the DC gain -3. So I'm going to do cross loop gain. I'm going to do DC gain -3. And then do edge 1. And I'll do falling. Then nil, nil, nil for these. Okay, and so that should give me my 2 calculations. I'll run my simulation one more time. How long is this getting? Ooh, it's gonna get kind of long. Thought I could do this faster. Okay, and now you can see it calculated my DC gain and my gain bandwidth for me, which are both in spec. So with that, we have done DC gain is good, gain bandwidth is good. Let's get our phase margin next. So to get our phase margin, we can go back to this. Oh, I lost it. Okay. You can use markers and measure it here, or what's easier is just go to Maestro. So I guess here, if you want to do that, then what you're going to do is place a marker on the loop gain, find where it becomes 0 dB, hit V right over top of that to create a vertical marker. And so that's going to measure, you can see the phase and the gain. So at basically 0 dB, you get 63.218 or 219 degrees. And in cadence, they start the phase at 180 degrees, and then it reduces down, meaning that to read our phase margin, we want the amount of degrees we're above a negative 180 degree phase shift. So in this case, a 180 degree phase shift, it can go from 180 to 0. So we can just read this right off the marker here, and that's our phase margin. If that doesn't make sense, review classical control theory. But I can also just auto calculate it by going to results, direct plot main form, check stability, check phase margin, and it'll give me a phase margin right here. And I can click add to outputs. And then I go back, now it has the phase margin. So I'll hit plot, and if I run, now it calculates my DC gain, my gain bandwidth, and my phase margin. Okay, next let's do the, so we did phase margin. Let's do our pole stuff for the closed loop. So I'm going to add a PZ analysis. For my positive, I'm going to do voltage. For my output, positive output node, select this output term or this output net. Negative, I'm going to do ground. And then for my input voltage source, make sure this is voltage, select, and I'll do this guy right here. Leave everything else the same, hit OK. And now if I run my simulation, and I think we did this back in lab 3. So should be pretty straightforward for you guys, but go results, direct plot, main form. And now I can go check PZ. I'll do poles and zeros. I'm not going to filter any of them. I'll do add to outputs and I'll put plot. So now this shows all my poles on I have the imaginary axis here and the real axis here. So I see 0. So my two dominant poles are this complex conjugate pair right here. So those are my dominant poles, and then you can see my next pole is way out here, and then I have some zeros and a pole, and then I have some zeros out in this right half plane. Anyways. Okay, so that's how you can show that, and then to find the pole queue, you can either calculate it from there, or what's easier is you can go to results, print pole zero summary, just leave everything default here and hit OK. And this will list all your poles and your zeros. And so your two dominant poles will be these first two. You can see they're a complex conjugate pair, and you can read off the Q factor from here. Note this is times 10 to the negative 1, so this is 0.737. So I'm a little high. I think I was going for like a plus minus 5% range or something when I designed this. So I could work to bring that down a little bit, but okay. So now we've done pole queue in the unit gain feedback configuration, and we've done this closed loop pole zero plot. And for the open loop pole zero plot, you just do the exact same thing, except take it out of feedback. So I'm gonna let you do that on your own because I think you guys have already done that. So we'll call that done. Okay, let's do some DC stuff. So let's do this ICMR, systematic input offset voltage, and then Quiescent power consumption. We'll do all of this at once. So for this, we're going to add a DC analysis. We're going to select sweep design variable, select our VS. Then we're going to go from VSS to VDD. So I'm going to use, you can type in the actual numbers, but I'll use this syntax here. Okay, do linear. Now I'm going to do a step size of 1 millivolt. And then I'm going to add thing to plot here. So I'm going to add an equation. I do VS, which is a DC voltage sweep. And then I'm going to do this output node here. Okay. And then I'll call this Vout DC. And then the next thing I want to do is I'll add another one, and I'll do IS, which is for current, select from design. And I want to grab the current from VDD here. And then, so this is going to be the current from the supply, and then I'm going to multiply it by, again, you can type in the numbers here if you want, but basically it's VDD minus VSS. So I'm going to do this var VDD minus var VSS, and I'll just grab the variable numbers, and that'll be good. And so this is my, we'll just call it power. Okay. And then if we'll just add the calculation now. So this Vout DC at VS equals 0 will be our input referred offset voltage. So I'll just do value Vout DC 0. This will be my DC offset. Okay, let's run the simulation. And you see, we're starting to get a lot of results here. So I'm going to go over here, and then I can click this little cards button, and then I'll show just this. And then I'm going to split this into two plots. So if I look at my Vout, I'm not going to lie, that's not quite what I was expecting to see. So I might need to check that. But This V out should be, oh yeah, okay. V out should be basically zero all the way across. And then you might see it like drop off, or in my case, rise. And so because we're, go back to the schematic, we have it set up so that this node is set to VS. And then there's a VS drop from this node to this node. So if our op amp has very high gain and it's operating, so if it has very high gain, then it'll force these inputs to be equal. So this will be VS, this will be VS, and then we'll have a drop of VS to here. So output will be 0 volts. If our op amp, if its gain drops off, then our things will fall apart and our output might not be forced to 0 anymore. And so basically it'll drop off when we become nonlinear, and we become nonlinear when we leave the input common mode range. And so our input common mode range is the range where output stays almost exactly at 0. And C mine extends all the way to VSS, and then it becomes nonlinear at about this point. We'll say maybe 1.5 volts. You can kind of just eyeball this, or you can add a calculation in if you want. But yeah, and then at 0 volt, at VS equals 0 volts, you can measure the DC offset, which is right here. So it's a systematic DC offset, not random. And then I can see my power is here, and it's pretty much constant all the way through. It's negative because I forgot to add negative sign. Cadence calculates current as going into the node is positive, going out is negative. And so because current is flowing out of this source, it's going to be negative. So I probably should have added a negative sign to my calculation, but it's fine. So yeah, so I'd probably just grab the value at 0 here, and that would be like about 154 microvolt or microwatts. It says amps. Cadence is not good at finding the units, so you kind of have to infer what it actually is. Okay, so hopefully that all makes sense. The reason this is the DC offset is that when VS is 0, then this terminal is set to 0, and this terminal is set to 0, or should be 0 as well, and so we'd expect the output to also be 0. So everything, because there's no drop here, so everything should be 0. But in reality, there's basically a little equivalent voltage source here, which models are offset. And so that'll mean that this is 0, and that voltage source makes V out something else. Okay, so now we've done ICMR, systematic input offset voltage, and then we did quiescent power consumption. Okay. All right, magnitude response of the amplifier and unity gain feedback configuration. So remember, our stability did the loop gain. Now we want the closed loop gain. So we'll add an analysis. We'll do AC. Once again, we'll sweep from 1 hertz to, let's say, like 100 megahertz. Logarithmic, 50 points per decade is what I like to do. And that'll be it. And then we'll add an output, drag it down to the bottom. This will be VF for a frequency sweep. And then I'll select on design and select this V out node. Check. And then we'll call this V out AC. And so now all we're doing is just a typical AC simulation where VS will be set to 0, VCM is set to 0. So we're at our common mode input point of 0 volts. And then we're doing just putting this in a unity gain buffer configuration and running an AC sweep. So I'll go ahead and run this. Okay, and I think our results popped up. So yeah, so you can use card to go to 1 and this little magic wand to go back to all of them. And I'm gonna go here, and for some reason it put everything together. So I'll just delete the loop gain stuff. Then here's my output. So I have a gain of 1, basically, out until about this point here. And if I want to, I actually should have put this in dB. So let's change this real quick. dB 20. And I want to save time, so I'm just not going to run these other simulations. And I think the goal is to compensate for maximum bandwidth with no peaking. So you can see we have almost no peaking here. We have 0 dB gain approximately. That's because it's a gain of 1, which is 0 dB. And then you can measure your bandwidth here to see what it actually is. And it should be about the gain bandwidth, but it looks like I might actually be a little bit higher. So that's interesting. Okay. Boom. That's done. And then last thing for this test bench, we'll do the signal to noise ratio. And this one gets a little weird. So we're going to add another analysis. We'll do noise, and then you need to set some bandwidth. I'm not sure what bandwidth would be the best, so I'm going to do 1 hertz to, I'll choose 10 megahertz. You could also do like 2.5 megahertz because that's like your gain bandwidth-ish, or I don't know. I meant to ask Geiger about what would be best for this. And I'm going to do 100 points per decade this time for more resolution. And then down here where it says output noise, instead of probe, hit voltage, then select this output voltage net. Go back, negative output node, select ground, go back, input source to voltage, just ignore whatever this is. And then select, I'll select this point here. And then we're not going to do noise separation for now, so hit OK. Then once again, I'm going to disable everything else and just do the noise. So now if I run my simulation, okay, we're going to go to results, direct plot, main form. And we're going to do input noise to get our input referred noise. We're going to do V squared over hertz. And click add to outputs, then hit plot. And so this plots our power spectral density of the input referred noise, which I think you guys talked about in class, but it's basically at each point here, it's the noise in a 1 hertz bandwidth centered on, so it's the total noise within a 1 hertz bandwidth using like an ideal brick wall bandpass filter, centered around this frequency. And then it sums all that and then puts it there. And so you can see this response here is from the flicker noise. It's kind of dominated by the flicker noise. And then once we get down here, it becomes dominated by the thermal noise. Now this gives us our power spectral density. What we actually want is our total input noise. And the reason we're doing input referred noise is that if we find the equivalent input referred noise, it's basically like if I take all the noise of the output and then I find what equivalent noise of the input when applied to to a noiseless circuit would give me the same noise of the output. That's what the input referred noise is. So if I find that, then all I have to do to find my signal to noise ratio is to just take the input signal and divide it by the noise, the input referred noise. If that doesn't make sense, there's I think Geiger talked about it, or you can look up like Razavi noise lectures. There you go. And then this video here. Of course, there's an ad. It's 2 ads. But there's like a series. There you go. This noise and electric circuits. Nope, never mind, not that one. Uh, this one, I think. Yeah, there's a lecture series about noise by Behzad Razavi, who's a very well-known professor and very smart guy, very renowned in the analog and RF field. So you can watch some of his videos about it. Okay. So anyway, so we want to actually integrate this because it's per unit bandwidth right now. So we want to integrate across this total frequency range. That'll give us the total noise in volts squared. And then we take the square root of that, gives us the total RMS noise, the RMS voltage at the input noise. So I'm going to go back and I added this to my outputs. I'm going to rename this so it's a little bit nicer. So I'll just do it input noise, add a calculation, and then you're going to do square root of the integral, so EINTEG, and then do input noise. You want to set the start point, so I set it as, I think it was 1 hertz. Your endpoint, I did 100 megahertz. And then for this extrapolating, you can just leave the extrapolation on right now. I don't know if this is the best way to do this, but this is the only way I know how to do it. So that's your calculation. And we'll call this the input RMS noise. And then if we want to calculate our SNR, the signal to noise ratio is going to be the input voltage in RMS. So it's a 500 millivolt peak to peak sinusoid. So in RMS, that's going to be 500 millivolts divided by square root of 2. And then divide that by our input RMS noise. And then let's put this in dB actually. So go to the beginning and do dB 20. And that'll be our SNR. Okay, so let's run this again. Okay, and get my power spectral density plot again, and then I get an input RMS noise of 495.1 microvolts, and then I get a SNR of 57.08 dB. Okay, so now we've done signal to noise ratio, and we've done, okay, so this is calculated based on stuff in the slides, so I'm just going to cross that off. And then all we need left is the slew rate and the output signal swing range. So I've done a previous video on output signal swing range. You can just follow that. Although I might do, how long is this right now? I might do a fancier way to do it here as well. But okay, so that's everything we can do with this test bench. So you can do all of those parameters in one test bench by basically doing that setup. So now let's make a second test bench. And to save time, I am going to just duplicate or just make a copy of this. Now I'll just make this number 2. Make sure I do update instances of new copies only to make sure my Maestro updates correctly. Okay. All right, now let's go to the schematic. Oops. Okay, so I said I'm doing slew rate. How I like to do slew rate is to actually put it in a, like, not unity gain, but something. I don't like putting in a unity gain because I can stress, or I can force the output to change faster, basically, with having some total gain. And then additionally, if I use it in a unity gain feedback configuration, then I might end up having my ICMR affect my slew rate. Now, in this case, we saw our ICMR was very, very large, but it could be problematic. So let's delete this. And now what we're going to do is we're going to put it in a gain of 10. So let me add this resistor, and I'm going to use a 10 mega ohm or 100 mega ohm resistor. It's probably a little larger than you need to do. You might want to do just like 100 kilohertz or something. Or actually, let's do this. No, I'll just do. Okay. So there we go. But you want it to be large to get around the output impedance of the amplifier. Actually, I'm going to do 10 mega ohms and 100 kilo ohms because that should be plenty. Okay. And then I'm going to delete these as well. And we're going to do a V pulse, which creates like a step waveform. So we're going to do DC voltage of 0. We'll do a voltage 1 of we'll call it negative amp divided by 2. We'll make this like so amp will be our amplitude, and this will be amp over 2. So this will create a square wave centered around 0 with a magnitude of amp. And actually, let's do it divide by 20. Because then what we're going to do is we can set the output amplitude that we want. And then because we have a gain of 10, it'll set the input to 10 times less than that. So that we can make it easier not to remember. Then we'll do a period of, let's just say 1 microsecond. That might be a little long, I'm not sure. We'll do a delay time of 0.5 microseconds just to make it a little bit nicer. Let's do this as 5. Like 2 microseconds. Okay. And then rise time we'll do, I'll just call it RFT for rise fall time for both of those. Okay, and that's what we need. So there's all the, let me show that one more time. Here's all the settings. Now 2 microseconds might be a little short, we'll see. Okay, now I'm all set up. So let's launch my ADE Explorer. Create, actually, wait, I'm gonna open existing view. And then I'm going to delete all of these tests. I'm going to delete all of the outputs that I have here. And then I'm going to click to add variable, copy my new ones. Let's do an amplitude of, our supply is 3 volts. So let's try like 2 volts. Is it? And a rise and fall time of, fast to go. We'll do 1 pico. That might be a little bit fast. Maybe 10 pico? I'll do 10 pico. Okay. And then I'll add a transient analysis. If I could find it. I'm an idiot. Can't find it. Oh, I'm on transient analysis. Okay, so our period of our thing is going to be 2 microseconds plus a 0.5 microsecond delay, and I'll just add 3 microseconds so we can see everything nicely. I'll do conservative. You can probably get away with moderate. Don't do liberal. It's too inaccurate. And then do OK. And then I want to plot the input and the output. So I'll do VT for transient voltage, select, grab the output, and I'll name this V out. And then, actually, I don't need the input. I just need the output. Let me just delete this. Okay. I don't know what that error was. Never seen that before. And now I can run. Holy crap. Okay. Well, this tells you I did not set this up well. So let's go back. And yeah, I can't remember how long I used to make these. So let's make this a period of 20 microseconds. Oops. We'll do a delay time of 1 microsecond. And then we'll leave all this stuff the same. Let me just double check to make sure I have everything set up. Option. Yeah, should be. Oh my goodness, my op amp is not op amping. What is wrong with this? I might have a bad op amp. Oh, I forgot to. No. Usually if your op amp is not op amping, it's not your op amp's fault. It's just your fault. Okay. I forgot to update this. So I did 20 microseconds, which means 25 micro. Let's save. Make sure we see everything. Oh, it's running again. Remember, if something seems off. It's probably your fault. There we go. Okay, so now we can see I hit. It looks like I'm not quite. Well, it looks like I set up my source wrong because I'm basically just saturating from rail to rail here. It looks like for my negative slew rate, I become very linear. It looks like, looking at this, I start pretty steep and then become less steep. So that makes me think I actually want to try to run this a little bit harder. So let's try changing this down to 1 pico. I mean, it's probably fine the way it is, but let's just run it like this. Okay. And so basically what I'm looking for is I'm looking for where this output is linear. And so it's straight and it's the steepest. And so if I look first at just this point here, I mean, I can't tell. I think I look a little steeper here, but I look pretty darn linear through here. So I'll just do a little two markers. A, B allows you to create a quick difference marker. And I can find my slew rate actually right here at the slope. It's the rise over the run. And so I'm getting 1.18 megavolts per second, or basically that's 1.18 volts per microsecond. And then if I zoom in on here, I can see again, I'm very linear. A, B, and I'm getting a falling slew rate of 1.19 volts per microsecond. So you can measure both of those and report them. And that's how you do the slew rate. I'm not quite sure why it's like fully going round and round. I probably also should have had you guys do the small signal step response. So we can look at that real quick. Change this to 100 millivolts. My rise and fall time is a little fast here. Probably want to make that larger. Okay, yeah, something's majorly messed up in my simulation setup. Or my op amp is crap. I'm not sure which. Okay. So yeah, I was thinking about doing a fancier method, showing you guys a fancier method of this, but just use the method I've shown in a previous video. So you can find that video for this. And then last thing we need to do is how to do this Monte Carlo simulation. And I'm sorry this video got so long. I was trying to do it in 20 to 30 minutes, but that was ambitious. So to do the Monte Carlo simulation, basically what a Monte Carlo simulation is is it uses statistical like distributions, let's say like Gaussian distributions. I think is if you look at the models, I think they use that for everything. So it uses that for like the MOSFETs and the resistors and the capacitors, and it models the statistical variation expected, like random variation. And then what it does is for each um, simulation run, it will sample a value from that distribution or distributions. So basically, it'll randomly generate a new circuit each time based on the expected statistics of the components to simulate with. And you can run like 200 simulations, and then you can look at the statistical characteristics of your design. Um, we're going to do a Monte Carlo simulation, 200 iterations to find the 3 sigma input offset voltage. So first thing I'm going to do is I'm going to close this, and I'm going to go back to my other test bench that I set up like this. First thing you need to go do is go into your design and don't copy this. If anyone copies this, you'll get 0 points. You need to replace all of your transistors with this PMOS 3 volts underscore miss for mismatch. I think this also has it miss. And then also for the capacitor, the underscore miss. So do that. Make sure you keep the same sizes and everything. And then I can open up my ADE Explorer. I'm going to only run my DC simulation, and instead of running a sweep, I'm just going to run it at 0 volts. So I don't need to sweep it. I'm just looking for the offset, which was at VS equals 0. So instead of sweeping it, I'll just leave VS set to 0, VCM set to 0. And then I'll add V out these or VDC, VDC of the output. This will be my offset. And then I can set all of these to not plot. Whatever, it doesn't matter. Okay, go to your setup, model libraries, and then here, instead of doing TT, you need to find, oh shoot, why is it not this list? Okay, you need to uncheck all of these. Grab this one that says, so add one, make sure it's the RF018. And then in here, you need to find like MC, for what you're looking for. So I'm looking for MC. So terrible looking these. Okay, MC MIM for my MIM capacitor. So I got that. Now I'm going to add one more. This I'm looking for MC underscore 3 volts for the Monte Carlo model for the 3 volt devices. So MC 3 volts, there we go. Okay, apply. And then go click this little arrow here to go up to AD assembler. Here where it says single run sweeps and corners, do Monte Carlo sampling. Hit this little or run button with a settings thing. Do standard Monte Carlo variation. You can do mismatch and process, do all 200 points. Save waveforms and save statistical parameter data. Hit OK. And then I'm also going to do the job setup, and I'm going to add more jobs because this is going to take a while. So then you run. And so what's going to do now is it's going to run 200 simulations. You can see down here it says 0 of 200 complete. So I'm going to let this run, and I will come back when it's done. All right, so this just finished. So now what I can do is go, so it shows me, it says errors because some things didn't calculate, but I can find my little offset here. It gives me the average across the 200 runs, the maximum, the minimum, and then the standard deviation. So this is your sigma. So you can multiply this by 3. That gives you your 3 sigma value. You can also do right click on it and hit histogram. And this will show you the distribution of the 200 sample runs. And it shows you the sigma, 2 sigma, and 3 sigma. So you can see here 3 sigma is on the positive side is 17.7622 millivolts, and on the negative side is negative 17.5343 millivolts. So the maximum of the absolute value of those two would be like your 3 sigma, or I guess just your standard deviation times 3 be your 3 sigma value. Okay, thank you. Have a good one. I gotta get going. Hopefully this was helpful.